Hi, and welcome back to Stats Online. Today we're talking about the normal distribution and the empirical rule. And we'll begin with a discussion of the types of data we see in this course. The first type, and the type that we see most often, the vast majority of our problems consist of, is what are continuous random variables. All right, these variables can also be called measurable or uncountable. All right, and basically, in theory at least, these continuous random variables should be able to take on any value within either a fixed interval or an interval that's infinite in one or both directions. All right, these are things that like ounces and weight and time, and in cases where fractions make sense is basically a continuous random variable. And even in some cases where we're dealing with data sets that are integer values, we'll treat them as continuous. Okay. The other type of data are discrete, which means that they're countable. In most cases, fractions don't make sense. And we're going to simplify our lives to really focus on mostly the type of discrete variable would be binary. So a binary variable is exactly that. It can take on one of two values. And when you put this in numerical form into an Excel data sheet or a spreadsheet, those values will be zeros or ones. So there'll be binary values. And the distribution of binary data is called the binomial distribution, which has a shape, a center, and a spread, a measure of variability. And we'll talk about that soon as well. And so, for example, if we're testing the percentage of blue M&Ms that Mars produces, we're looking at cases where either an M&M from a sample or a population, doesn't matter, is either blue or it isn't blue. And you can imagine with a spreadsheet that you mark a 1 every time you encounter an M&M that's blue, and a 0 any time that you encounter an M&M that's not blue, any of the other 5 colors. That would be a binary data set. We'll start with continuous. And I have this kind of leading question. Well, sample statistics, and notice again SS and PP here always equal population parameters. Remember, sample statistics are your estimates of population parameters, and in real interesting questions in statistics, it's those population parameters that are unknown, but I'll remind you from a previous lesson that we start knowing some values in this population so we can get a handle on what these distributions look like, and then we'll start taking away this information and only deal with sample data. The answer here is no. Hopefully that's obvious, is that we're only taking a sample from the population. And so the mean from that sample will likely not equal exactly the mean from the population. So you can see here x bar minus mu, this difference is called sampling error, and we'd think that it's something non-zero. It could be small, it could be 0, okay, but it's not likely that these two values equally, the parameter and the statistic equal each other. However, we want to be able to say something about the likelihood or the probability that a given event may occur, the probability of getting a certain data value or sample data value. And probability distributions like the normal distribution or the normal curve or the bell-shaped, however you want to call it, all these different synonyms, all these different names for the same thing, the bell-shaped curve, the normal curve, these things, this shape represents all the possible events, and under that shape or within the graph is the area, and that's the probability of these events occurring. And so we're going to use the normal distribution quite a bit. So continuous random variables, I've already introduced that they're uncountable, that there's a continuum of values, that any value can occur in that range. Fractions make sense. And this part may take a few seconds to convince you of this, but if there are a continuum of values, right, or there are infinite possibilities within a range, or even if the range is undefined, then what the second bullet point is saying here is that the probability of a single event occurring is about 0. And the way we're coming in my example there is this capital P probability that x equals 29.25 exactly is 0. And that's the kind of relationship we would be looking at. And the reason for this this equivalence to 0 is that the probability of getting exactly 29.247, and we could keep going on fractions in terms of decimal places rather, is that this is one particular value. This is the frequency of 1 here over however many possible values there are. And if I'm saying that there are infinite possible values in a continuum, that's 1 over infinity. And that's a 0. All right? And so we will not be able to, if we have continuous random variables, we are not able to say that there's a positive likelihood of any single event occurring. Okay? You can imagine if you were measuring some sort of volume and or ounces, let's say, and we could go on to any decimal place, the probability of getting exactly 13.69758 ounces is going to be 0, because that's one value out of infinite number of possibilities, and so the relative frequency, 1 over infinity, is going to be 0. Thus, the takeaway message from this whole slide is that we calculate probabilities for intervals. For continuous variables, we do not calculate probabilities of a single event, because those are going to be 0. So in notation form, the kind of questions we can answer, the kind of probabilities we can get a handle on, are like this. The probability capital P that X, whatever value that is, this could be miles per gallon, let's say, of a vehicle, is between 25.5 and 30.75. That's something that we can calculate. That's an interval. So the normal distribution, many of us are familiar with this. It is bell-shaped. One of its properties that is perhaps more subtle is that it's asymptotic in terms of its approach to the horizontal axis. It never quite touches that in theory. And so the normal curve asymptotically approaches the horizontal axis. I mean that, out into the tails, a normal distribution still goes on. It's just that the likelihood of those events becomes smaller and smaller and smaller. The area under the curve, however, is approximated as 1. The bell-shaped element of the normal distribution implies it's symmetric. The symmetric element implies that the mean and the median are equal from a previous lecture. 50% of the values are above the mean, 50% of the values are below the mean. And we could, of course, flip that on its head, and instead of talking about percentage of values, we could talk about probability. So the probability of getting a value above the mean, the probability of any value, okay, occurring above the mean is 0.5, or less than the mean is 0.5. And in this case, I say greater than 0 only because in our graph here, the mean, that center line that divides the distribution into symmetric halves, is 0. We'll go back to that in a moment. Here's that moment. So the previous slide, note the values for the mean, mu, and lowercase sigma, the standard deviation. If you go back here, you see that the mean is 0 and the standard deviation is 1. All right, each of these tick marks represent a standard deviation away, and we have increments of 1. So mu equals 0, sigma equals 1. If we have a normal distribution with those two properties, we have a specific type and a very important form of the normal distribution called the standard normal distribution. All right, and it turns out that any distribution of data that is normal can be standardized so that the mean is 0, standard deviation is 1, and it will allow us to actually go on and to use the cumulative z-table. But before we do that, let's look at the empirical rule, which again should be a review. The empirical rule has three parts. It says that, okay, if you have a normally distributed data set, then 68% of the values are going to lie between one standard deviation above and below the mean. All right? This is independent. If it's ounces, time, miles per gallon, weight, height, grades, whatever we have for continuous variables, if this is the case, then 68% approximately, all right, I think it's 68.44%. If you look at any textbook, they'll usually give you the percentage up to 2 decimal places, or the zero, when we're rounding up to 68% here, or in this case, we're rounding down. Approximately 95% of the values lie between 2 standard deviations above and below the mean. All right, and almost all, virtually all, it's less than 100%, but it's pretty close. I think a 99.7 or something. Almost all data values rest between 3 standard deviations above and below. Okay, so observations are possible outside of 3 standard deviations, but unlikely. And we can use the empirical rule to kind of get a handle on that, at least in a very broad brush form. Here are some questions requiring use of the empirical rule. So variable x is normally distributed with a mean of 3 and a standard deviation of 2. Determine the upper limit for an interval around the mean, okay, above and below the mean, that contains about 95% of the x values. So the 95%, we're looking at the second part here, that 2 standard deviations above and below the mean. And so the upper limit will be on the right-hand side, so that's going to be the mean plus 2 standard deviations. And so that's 3 plus 2 times 2. And so 3 plus 4 is 7. So that's one use of the empirical rule for that question. How about probabilities for a normally distributed random variable? Here we're talking about 95% of the values. Well, to get probabilities of a normally distributed variable for any range, it's possible that we could integrate under a normal curve. Okay, we could find the area under that smooth distribution. And in fact, this would be the formula we would use, the probability of x between A and B, right? Weakly less than B and strictly greater than A. However, we're not going to have to do that. For some probabilities, we can use our knowledge of the empirical rule. And you'll see that for other probabilities, someone has done this very nicely. Someone has done this integration for us. And those integrals, those areas, okay, are contained in the Z table that will be posted on the course website. But let's use what we already know. The empirical rule in the 2 slides ago was given in terms of the percentage of data, but we know that there's this one-to-one relationship between percentage of data and the likelihood of an event occurring. And so let's rephrase the empirical rule in terms of probabilities. So the probability is 0.68 that a value falls within 1 standard deviation of the mean, all right, above and below the mean. That's just relying on the fact that 68% of data values are there, so the likelihood of one observation falling within 1 standard deviation of the mean is 0.68. An observation falling within 2 is 0.95 as a probability, and the probability of the likelihood that an observation is within 3 standard deviations of the mean is pretty much 1, right? It's approximately or approaching 1. That's the empirical rule as restated in terms of probabilities. So what's the area? What's the probability for this particular shaded region? We can use the empirical rule. We're going to actually use a couple elements of it, or 2 parts of it. And again, probabilities are going to be between 0 and 1. And so the answer is 0.815. How we get there is that the area between 8 and 10 is half of the first element of the empirical rule. First element being 0.68. This is going to be 0.34. And this, of course, is 0.475. This is half of 0.95. And so if you add both elements together, you're going to get 0.815. So I encourage you to convince yourself that this is true. Notice that this particular distribution, we can, just from the picture, recognize that the mean is 10 and the standard deviation is 2, all right? Because just from the tick marks, without any information, more information given up here, we can see that the distance between tick marks is 2, so that's the standard deviation. So for instance, the question could be, what is the standard deviation for this distribution? And hopefully it's apparent that it has to be 8. This is the first element of the empirical rule for this particular question. We're again using half of the first element of the empirical rule, so this is going to be 0.34. Notice the notation, right? P, capital P, probability of x being between 8 and 10. Here, we're going to use, we need this area here, the probability that x is less than 1, but we're going to use what we know about the area we don't need. And so the area above 5 is 0.5, above the mean is 0.5, and this is going to be 0.34. So we know that this area shade is going to be 0.16. Right, so you see that where this says the interval begins with 1 standard deviation to the left of the mean and goes to negative infinity. This is 0.34, this is 0.5, and so the complement of that is 0.16. I say it's a complement rule, but it's just 1 minus the area we don't need. Now, beyond the empirical rule, okay, you know, these examples are nice for finding intervals that fall nicely within 1, 2, or 3, or any kind of variation of that standard deviations under a normal distribution. But what about finding the area between, you know, 0.3 standard deviations below the mean up until you know, 1.73 standard deviations above the mean? Well, we're going to need to be a little bit more precise than the empirical rule, and that's where we're going to use the z-table. Okay, and the z-table is also called the standard normal out table because the z-table is just a standardized normal distribution, a normal distribution with it that's transformed so that the mean is 0 and the standard deviation is 1. The version of the table we use in this course, and it's not the only version, is posted as a PDF on the course website. I should say that it's the cumulative normal distribution. It's going to have the left side and the right side. Okay, so it's going to have negative z's and positive z's, and it's going to allow us to look at the distribution in its entirety without relying on any sort of properties of symmetry, where some tables present half the table, half the normal distribution, recognizing that one side is the mirror image of the other. All right, if you use either table correctly, you arrive at the exact same answer. I choose one that I'll use in my course materials, and so I encourage you to use that one as well.